Hi all, and welcome to Mr. Hunter's physics lessons. We're going to go through the photon model for chapter 13 of the OCR spec. So we're going to start with quantum physics, and lesson 1 is the photon model. Let's just jump straight in. So we know that light, it's too large. So we know that light behaves as a wave and particle. The wave nature of light was demonstrated by Young's modulus experiment, Young's double slit experiment. Oops. And the particle nature of light will be demonstrated by the photoelectric effect, which we'll cover later. But for now, we need to look at the particle nature of light via an equation. So a photon is a particle of light. Particles of light, and all particles are quantized bits of matter and energy. So a particle here, we can say that this particle is quantized. So it has very specific energy values. So what do we mean by quantized? We mean can only have specific energy values, and these energy values are given by the equation E equals hf. So let's have a look at this a bit deeper. E is energy in joules, F is frequency in hertz, and H is Planck's constant, named after Max Planck. And Planck's constant is measured, if you do the analysis, is joules divided by hertz, which is joules divided by 1/seconds, which is the joule second. And so what this tells us is that the particles of light, or light, can only have energies given by the ratio of H. And it also tells us, quite importantly, that the energy of a photon, or energy of light, only depends on its frequency. And if we recall that fluffy lamb's formula, C equals F lambda, then because C is a constant, F is C over lambda, we could plug this into that equation, or E equals HF equation, and this leaves us with E is equal to HC divided by lambda. And so you could also say that the energy of a photon only depends on wavelength as well, but because the speed of light is a constant, it, depending on frequency and wavelength, is the same. We're saying the same thing. So the value, and you don't need to remember this equation here, this is given to you in the formula booklet. So the value of H is 6.63 times 10 to the minus 34 joule seconds. And so this value here gives us the quantized energy value of a photon. And so we can perform calculations. I could say, if I have a gamma photon and we can say this has a frequency of 2 times 10 to the 20 hertz, then what is its energy? Well, we can just plug in E equals HF. H is a constant, multiplied by our frequency, and it spits out a value of 2 times 10 to the minus 13 joules. And so clearly this is a small number, it's a small amount of joules. And so perhaps we need another unit to express our energy of photons in sort of more sensible, or even just the energy of any quantized bit of matter in more sensible units. You don't want to be writing times 10 to the minus 13 all the time. So this brings us to what's called the electron volt. And so we're on a new little subheading here, the electron volt. And so we need to define the electron volt. The electron volt is defined as the energy change of an electron when it moves through a potential difference of 1 volt. So if we remember that a volt is a joule per coulomb, it's an energy per unit charge, then we can say that 1 electron volt, little e, big V, and you must get it that way round, do not mix those up. 1 EV is equal to 1 joule passed through a coulomb. And so then 1 electron volt would be 1 joule per unit coulomb of an electron. If the general definition is a volt is a joule per coulomb, then 1 electron volt is a joule per unit charge of the electron. The electron has the fundamental charge of 1.6 times 10 to the minus 19 coulombs. So this ends up becoming 1.60 times 10 to the minus 19 joules. And so this helps us shrink down the numbers and makes them easier to write. So if you wanted to convert, let's go back to blue. So if you wanted to convert joules to electron volts, what would you do? Well, you would divide by 1.6 times 10 to the minus 19. And so let us convert our previous answer of joules. So we had 1.2 times 10 to the minus 13 joules. In electron volts, this is equal to 1.25 times 10 to the 6 electron volts, which is the same as 1.25 mega electron volts. And you'll often see this start to come up pretty much everywhere from now on, is that we can express in electron volts and then we can express in MeV. And so a lot of particles will, and it's just by convention that particle physicists, both theoretical and experimental particle physicists, will express their energies of their particles, including the photon, in mega electron volts, or just MeV. And actually, it is quite useful because it keeps the numbers quite simple.